Okay.
Every day, Connor gives me a new song to do stuff in your head.
So today we're going to talk about rolling friction.
Rolling friction.
So what causes objects to roll?
Gravity.
Well,
Bending of space.
there's no friction here. I've turned friction off. Ignore the guy at the top. Just look at this guy. Turn friction off.
Nothing.
So he's not sliding. He's not rolling. There's gravity here, but he's not rolling.
Oh, so friction.
It's friction,
Causes roll.
right? The only difference here is going to be I'm going to turn on some friction.
More technically torque. I mean, couldn't you put other kinds of torque on it and then it would roll?
But you'd have to have another force. What other force would be? If we're just letting it drop, if we're just letting it go down a ramp?
Like a jet engine?
Oh, I understand. I just.
Well, yeah, if you put a jet engine on it, it would. So when I hit play now it starts to roll. And we don't see the friction force unless I really blow up, because in relation to the normal force in mg, that the friction force that causes rolling is typically pretty tiny. But if I blow this up enough, there I see the friction force right here. And it is acting here. And it is acting a distance away from the axis of rotation. It doesn't matter that it's rolling down. It maintains the same position relative to the axis of rotation. And so that friction force will cause an increased angular velocity, as the object also picks up an increased linear velocity, right?
So would that technically mean rolling is slower than just sliding down by like a microscopic?
Yeah, and we're going to talk about that today. Yes, you have good insight.
So rolling is just kind of the wheel falling forward on itself.
Yeah. Yeah. It's like if you were to stand there and I came up behind you and just pushed you and you went like that. Yeah, because the axis of rotation would be where your feet are toes are in contact with the ground, and then the rest of you would rotate about that point. And so, yeah, that's a good analogy. So a rolling object is just going to be continuously doing that. Yeah. I'm going to keep that.
Thank you.
Does
All right.
a rolling object
And take credit for it, too.
Trademark.
Does its angular acceleration larger than its.
Say again?
Does its angular acceleration increase?
No. If the friction force doesn't change, then the angular acceleration will remain constant.
Okay.
And so therefore, the linear acceleration also will.
It's just the angular velocity increases.
Yes. Okay. So let's look at that in a little more detail. And a typical problem might have you actually calculate that friction force. So here I got. Oh, that's not spherical at all. You're scaring me back there.
I'm saying.
The water went down.
Go get water if you need to.
It went down the wrong.
Oh, went down the wrong pipe.
Yeah.
Okay. Could you cough more quietly, please? All right, so let's draw our free body diagram here.
I'll die quieter.
I got my weight force mg. And I'm going to be kind of careful here. I'm going to draw the forces where they're actually applied because we do have rotation. So this is essentially my free body diagram. Technically, the normal force acts on the bottom surface of the ball, and the friction force acts up the ramp. And I'm exaggerating the friction force here just so we can more easily see it. Is this static or kinetic friction? Static. Just because it's rolling doesn't mean it's kinetic friction. If you look at the contact point, they are in static contact between the wheel and the ground. And if it was kinetic, then it would be sliding. And we'll actually talk about that. We'll talk about that later today.
Isn't it a separate kind of friction, like rolling friction? Because if it's sticky, like is that also a factor in there?
Yeah, it would mimic like a friction force. It'd be similar to a
Is it
friction force.
exactly the same as normal, like static friction, or are there different in any way?
There's probably subtle differences, but you would be able to treat it like static friction. Okay, so
Surfaces are like very different when they roll. Maybe.
say again.
Are there like really weird surfaces that are different when they roll?
Probably. Okay, so let's say that this is the question, it says find the friction force and express it in terms, I spell terms, of m, g, and theta. Okay. And just kind of follow along here, like this is a typical type of problem, but just kind of follow along. What do we need to do first? We are dealing with forces and torques now, so we're just still dealing with Newton's laws. I probably want to define a coordinate system.
Yeah, I was about to say draw a free body diagram, but we already did that.
So the next step would be, based on my coordinate system and the free body diagram, to
The net force is labeled.
before that,
We'll decompose that.
let's decompose the vectors. So I decompose mg. Oh, this is a very nice brand new marker. And I know it's been a while since we did ramps, but this angle right here is congruent to the angle of elevation, making the down the ramp component mg sine theta, and this one mg cosine theta.
It's cos.
Cos theta, if you're a weirdo. All right. So we have that. And now realize that now when we have things, we have two spatial dimensions where stuff's going on, and we also have a rotational dimension. So we can get three equations now, right? Before rotation, we can only get two equations for objects moving down ramps. Now we could potentially get three. I start with the one. I like starting with the one that's relevant to what the question is asking. So I'm going to start with what direction? It's asking for the friction force. The x direction. So I will say the net force in the x direction equals the mass of the object times the acceleration in the x direction.
So mg sine theta minus the force of friction equals ma.
Yep.
Yeah.
Good. I'm just going to put ma. We know it's in the x direction.
Yeah.
That's the only direction it's actually going to linearly accelerate. Yeah. All right, well, we can put that in our equation holster, as Mr. P from Flipping Physics likes to say. Because really, we can't solve for, what's our problem?
Solve for the friction.
In terms of
mg and theta.
we have an a.
We have an a that we need to get rid of. Strange, because the net force in the y direction doesn't have acceleration. So that's not going to help us. We might need to do that by the end, but so how can I get an expression for acceleration? Another expression involving linear acceleration. Couldn't we use torque to get an expression involving angular acceleration?
Yeah.
And then realize that linear acceleration is the radius times the angular acceleration?
That's exactly what I was thinking.
Now understand that this is only true when we're talking about the angular acceleration of a point on the or a linear acceleration of a point on the rim. And what you need to do is understand this. We went over this last year and had a little setup up here. But whatever linear acceleration an object has as it accelerates around the outside is the same as the linear acceleration of the center of mass. Right? The rate at which this guy is moving about the center is the same speed as the rate, same as the rate at which the center of mass is moving down the ramp. And if we have time today, I'll give you a little demonstration as to why. If not, I will tomorrow. But just understand that. The speed that it has down the ramp, the acceleration it has down the ramp is the same as the speed or the acceleration that a point on the edge is going to have as it moves around. All right, so we can use torque. The net torque is equal to the rotational inertia times the angular acceleration. What is this? This is a pulley. This is a pulley. So the moment of inertia is 1/2 mr squared. All right. And I'm going to go ahead and define into the board as my positive z direction. I'll put a little x there. positive z direction, so that the acceleration in this direction will be positive. Okay. So that the torque created by the force, the friction force, will be positive.
Because the it's going into the
What?
nothing.
Okay. So the torque here is due to the friction force, so it's going to be the friction force, times the lever arm, which is drawn from the axis of rotation to the point at which the force is applied, and that has length r, times the sine of the angle between those. What's the angle between those? 90. What's the sine of 90? 1. So it's just this. That's going to equal 1/2 mr squared. And then we can substitute in, if A equals R alpha, then alpha equals A over R. So instead of alpha here, we can substitute in A over R. And notice what happens.
One of the R or both of the R.
Both of the R's.
Cancel.
Wow.
All R's cancel.
All of the R's go through.
Right? Both terms brought one R to the party, and then this guy's got that. So we get a nice expression, the force of friction equals 1/2 mass times acceleration.
A little bit though.
What's that?
Gotta change things a little bit though.
That'll change things a little bit?
We have to.
Like solve for A.
Oh yeah, you have to solve that for A. So I multiply both sides by 2, divide both sides by m, get that the acceleration is 2 times the friction force, divided by the mass m. Right? So then I just plug that dude in for the acceleration here.
Mr. Figure it out.
Oh my gosh. So I get, when I plug that in, I get mg sine theta minus the friction force equals the mass times 2 times the friction force over the mass.
So M cancels there.
M cancels there, but not everyone brought mass to the party, right?
No.
So I get that mg sine theta
Equals 3F.
equals 3f. 3 times the friction force. I just added it to both sides, right? Divide by 3, so I get that the friction force will be mg sine theta divided by. So mg sine theta, notice, is down the component that points down the ramp. So the friction force will be 1/3 of that pointing up the ramp.
Not too small.
It's not too small, yeah. Cool beans? This is what's referred to, by the way, as rolling without slipping. Or sliding. Or skidding. Rolling without slipping or skidding or sliding.
Perfect rolling.
Perfect roll. Perfect roll.
I was thinking that would probably happen in here.
Yeah, it happens often. You want this happening whenever you're driving.
You're not just gonna
You
do
do
not
not
do a burnout.
Because if your tires are rolling and yet, well, burnouts, yeah, burnouts. As we'll learn though, if you're burning your tires out, you're not getting the maximum acceleration that you could get. Yeah, if you're wanting to be safe and not race, then you want your tires to be rolling without slipping. Because if they're slipping, then you're probably, if you're in motion, and especially if you're turning, you are skidding, right? And you endanger yourself and others.
That's what black ice does to people.
Mm-hmm. It significantly reduces the coefficient of friction, static friction, which greatly reduces the maximum velocity you can take a turn in without skidding, as you learned last year, right, Connor?
Water just causes so many problems, doesn't it?
It does. We should just get rid of it.
Ban water.
We should ban it.
Dihydrogen monoxide.
Dihydrogen monoxide, yeah.
They were like talking about how it like burns in its liquid and gas form, and like how like there's so many kids that die from it every year. So Like, our science teacher asked a class if we should ban it, and then made us all feel stupid.
Did they take a poll and stuff? And
Yeah.
okay, yeah, they did that at my college when I was in college.
Happened this early.
Yeah.
Yeah.
Okay, so let's talk about. Does that make sense? Everything we just talked about. That's rolling with slipping. What do you think we're going to talk about now?
Rolling with
I know that's rolling without slipping.
We're talking about rolling with them.
We're going to talk about rolling with slipping. So here's a nice video.
They show a
Oh,
video
that
of
makes
a
Oh, bowling.
That's.
That's very
Ah.
slippy.
Did you see the transition?
Yep.
It transitioned from rolling with slipping to rolling without slipping.
Wow.
Right? After it went a certain distance. At the beginning, it is rolling. Try to ignore the he tried really hard. It's really hard to get it to move with an initial velocity with zero rotation. But there was almost zero rotation in the direction of motion. And the friction force is acting on the ball now. And it is a kinetic friction force. That kinetic friction force is creating a torque that's causing it to increase its angular velocity. And eventually, that angular velocity will correspond exactly with the linear velocity in such a way that it will no longer be slipping and it will then be rolling. This,
Hit the
It will
pins.
be a static.
what's that?
Did he hit the pins?
Oh, I don't know. Yep.
Hey.
That's all I need.
I tried to pause it right before and say we'll never know.
Score
We'll never know.
and,
So that's rolling without slipping. I made a little simulation for it too.
no, it was rolling with flipping.
That's rolling with slipping. That's what I said.
No, you said without.
No, I said with.
You said without.
You weren't listening.
Yeah, it will be.
You must have missed the word.
Yeah. Okay, so here, it starts moving and it is rotating. Notice, what I should say, look at the speed here. The speed will be reduced because the friction is a net force that's going to slow it down. But the angular velocity down here will increase. It will increase in the negative direction because Algodo does use the typical convention. And so as it goes, that's why I slowed it down so we can watch those. As it goes, and then eventually, it stops accelerating. And turn off air resistance. If you let it go far and long enough, then the friction force will start to slow it down, but it takes a long time. So at this point, it just kind of rolls with the same speed. Actually, maybe this will make it a little easier to see. Let's see. And then eventually, bam. Now it's nice and settled down. So the point at which the angular velocity becomes constant is essentially the point at which it's rolling without slipping. Yeah. So there's a transition point there, right? Okay. So this is going to be the problem that those at home are going to have to solve along with me and submit for attendance for today because we don't have a new assignment today. So,
Oh, Mr. Graham, I might be going online soon. I'm just being really worried about all the COVID.
okay. Well, that's unacceptable.
You better be the one that comes in on the Zoom class. Every day. We're going to be looking for you. We're going to ask where you are.
And all of us will text you if you're not.
This is all not true.
You will be spammed beyond belief.
This is all not true. Let me know if they're being jerks and I will give them all zeros. Okay. So I wrote this morning and didn't want to erase it because it took so long to write. But here's the problem. A bowling ball of mass m and radius r skids down the lane with initial speed v0, but with no initial angular velocity. So it's like the simulation here. It starts off with an initial velocity purely horizontal, and then it will start to roll with slipping, and eventually it will roll without slipping. Find the distance the ball skids before rolling without skidding. So, i.e., find the distance it's going to go until it's rolling without skidding. In terms of the given quantities, fundamental constants, and the coefficient of kinetic friction, mu k. We must know, by the way, that we are dealing with a bowling ball, which it's not a solid uniform sphere, but let's pretend it is. So the rotational inertia for a solid sphere is 2/5 m r squared. You can determine this now by doing the integral. That's a tough one though.
In that
Spherical shells instead of just thin hoops, you know.
So that's what we technically have to do for the AP exam, right? So if we had like a
You're not likely to actually have to, not for a sphere. You wouldn't. I've seen rods. I've seen having to determine the rotational inertia for a non-uniform rod.
Okay.
But yeah, for a sphere, probably not. Yes, sir.
So, when it's skidding, it has kinetic friction, but when it starts to roll perfectly, it has static friction?
Yes. Yes.
So are we solving for when...
We're at finding the distance that the ball skids before rolling without skidding. So we're only dealing with the kinetic friction.
Okay.
Because once it's rolling, once the static friction has taken hold, then it's traveled the distance that we're being asked to calculate.
I have a small question about the rotational inertia for like a shell, like a spherical shell. Does the thickness of the shell matter?
Yes. Yes. So a spherical shell is assuming that the thickness of the shell is very small in relation to the radius. Because something like this as compared to this, notice how the thickness of this guy is much smaller in relation to the diameter, the actual dimensions of this guy. This one's much less so, right? This is pretty thick, and the radius is smaller. So the thing is that in reality, you can't neglect it completely. And so there's a different formula for the rotational inertia for a hoop that is not thin, right? And so the same thing applies to spherical shells as well. So the ones that you see on your formula sheet there, like this, the rotational inertia for this guy will take into account the outer radius and the inner radius.
Oh, okay.
But in this class, you don't really deal with that stuff. So that's a good question.
Beyond the scope of this class.
Beyond the scope of this class. All right. Let's see if I can do this. I always have trouble with this one. This is a tough problem. So we have a bowling ball that is rolling, has an initial velocity v naught, and remember omega naught 0. We have obviously a weight force, but we really don't need to worry about it. A normal force, again, we really don't need to worry about it. The friction force is what we need to worry about. And this is a kinetic friction force. Because it's rolling. First of all, it's not even rolling, but an instant later it will be rolling slightly, but it will be skidding at the same time. So there will be that friction force there. Okay? Y'all with me? And that friction force is a distance r, where r is the radius. Am I using capital R? Yes. Capital R, distance from the axis of rotation. Okay. So I got my free body diagram drawn. I am going to be looking for a distance. So if I'm looking for a distance, what am I eventually going to have to do? Kinematics. Right. Because when we do Newton's laws, the only kinematic variable we can determine is acceleration. Then if I want to know how far it's going to go, I'm going to have to do some kinematics. But I definitely don't have enough information to do that right now. Right? There's two. We can put these in our equation holsters. There's two equations that we could potentially use to figure out how far it went. And we can use either one of those to find what x is and just call x naught 0. Right? So we definitely don't have remotely enough information to use those equations now, right? So what should I do you think? Newton's laws, yeah. And I can use Newton's laws for the horizontal motion and Newton's laws for the angular motion, the spinning motion. So let's do the straight liney stuff first. So I'll say the net force in the x direction. Let's define my coordinate axes. I'll say to the right is positive x, to the up is positive y, And then I want friction to cause a positive torque just so I can minimize the negative symbols. So I'll call into the board the positive z direction. So I do a little x, right? So my net force in the x direction is going to equal the mass times the acceleration. This acceleration here. In the x direction, what forces do I have?
The force of friction, kinetic.
The negative
Yeah.
force of kinetic friction equals mass times acceleration. But remember, mu needs to be in our answer. Friction force itself can't. So
F negative mu Fn.
negative mu kinetic times the normal force equals mass times acceleration. And I know that the normal force, this is technically analyzing Newton's laws in the y direction. But really, all I need to know is that the normal force is mg equal to mg. So negative mu k mg equals ma. Everybody brought mass to the party. So look, now I have an expression for a kinematic variable, right? A linear kinematic variable. I know that the acceleration is equal to negative mu k times g. So that can go up into here, right?
Neither velocity or time.
We have initial
And probably final velocity.
Yeah, we don't have
Well, if
final
you-
velocity, we don't have, and time we don't have.
Oh, time. Yeah.
Maybe time.
We can probably solve for
Oh.
You probably get time from the.
The first kinematic equation.
Well,
Well, not wait, like the.
we would. That's why we have three different kinematic equations. We're not going to be able to get anything else from just the x direction motion. But isn't time a scalar that is common to all, both the x and the y direction motion and the spinning motion?
Yeah.
So maybe let's try to find the time using the spinning motion. Okay? So let's just analyze the net torques. The net torque is going to be the rotational inertia times angular acceleration alpha. What force is causing the torque? The friction force. So the kinetic friction force. And it's not negative now, right? Because I'm considering, I said that this guy's creating a positive torque based on my chosen coordinate axis. Times the lever arm, which is the radius. Times the sine of the angle between them. 90 degree angle, sine of the angle is 1. So it just simplifies to this. That's going to be, now the rotational inertia is this guy right here. Get used to making this substitution though. The angular acceleration, I can tie in with these equations as well by putting A over R. Okay. So I can make that substitution, so I get the I, which is 1/2 m 1/2 mr squared times A over R. What happens again? R's cancel.
Bye bye.
Actually,
Yeah.
that does happen. I'm sorry, I forgot to point something out. I knew this was going to happen. Trenton, this is all your fault. I knew this was going to happen. Before we go on here, yes, what we were doing is correct. But it's something that'll make our road to the solution a little longer. So let me point something out. This is something I should have pointed out first.
Oh,
The condition, so this is a red star. The condition required, and this is required for rolling without slipping. The condition that, this isn't grammatically the best, that relates the translational, and I knew I was going to do this, and I still did it, and angular motion. So we have to recognize a condition that must be at play, and this will allow me to then modify my approach. If this guy is moving, rotating without slipping, and is not accelerating, let's just say it's rolling with a nice constant velocity, then the relationship between the final angular velocity and the final linear velocity is this. Right? If that is true for a rolling object, it is necessarily rolling without slipping. Okay? That means that a point on the rim, as it moves, has the same velocity as the actual object that is as it's moving translationally. Okay? So this is the condition required in order to have rolling without slipping. Sorry, I should have started with that. Because when we have that condition, then we can say, I can get a nice expression for final velocity, because I need final velocity and expression for it. Final velocity is going to be the initial velocity plus the acceleration times time. That's kinematic equation number 1. I'm real sorry, guys. I messed this up. I'm going to blame Timothy today. And then the initial velocity is not 0, so I have an initial velocity, and then my acceleration is minus mu kg. So minus mu k times g. Times time. Okay. So here I have an expression for v that I can plug in here. And then I want a corresponding equation for omega that I can plug in here. And then try to solve that for something that will allow me to figure out the distance that's traveled. I've never seen a question like this on the AP exam. But you want to understand the physics here to make the types of questions that you might see a little more doable. So why I say that is because I actually want to solve this for angular acceleration so I can get a similar kinematic variable for final angular velocity and plug that into this guy here. Okay. So net torque, it is the friction force, kinetic friction force, times the radius equals 2/5 m r squared fishy, but then I want to solve this for fishy. So one radius multiplied by 5 halves, 5 over 2 mr squared. So I get 5 times the friction force. The friction force we know is mu times the normal force, right? Or mu mg. So 5 times, I'm rushing ahead now. Mu k mg equals 2/5 mr squared alpha. Why don't I just have this in front of my face when I do this, Joel? Why don't I do that? And then I see that the masses cancel.
Shouldn't be mr squared, it should be mr, right? Because one of them canceled earlier. Or
Yeah.
75.
Where are you seeing that too? I see no 2. I make one mistake and then it's all downhill. Alpha then is going to be 5 times the coefficient of kinetic friction times g over 2 times r. Okay. Oh boy. And then I can use the same kinematic equation, which doesn't involve distance, by the way, right? I'm just solving for these kinematic equations so I can plug them in here in order to determine essentially the value for t that I need up here. So I can say that final angular velocity equals initial angular velocity plus the angular acceleration times time. Initial angular velocity was 0 because it wasn't rotating at the beginning. And then I can plug this in for the angular acceleration. So final angular velocity is 5 times the coefficient of kinetic friction times g times the time over 2 times r. Now that I have expressions for v and omega, I can then say, well, I have v equals r omega. For v, I can plug in, actually, I'm going to put that up here. v equals r omega. v naught minus mu k gt equals the radius times 5 mu k gt over 2r. And no one brought there's nothing that was brought by everyone to the party, right?
R's.
But I can cancel those r's there.
What about G?
There's no g in the v naught term.
Oh, right, yeah.
So I have V naught minus mu k gt, and then after I write this, I'll tell you why I'm doing this. 5 mu k gt over 2. When I look at these equations, like you already noticed, and I've tried solving it the way that we were starting to, that's why I started to do it that way, and you end up hitting a roadblock. So just to avoid the time that it would take us to avoid that roadblock, I stopped and I kind of reassessed. If you substituted A over R in for this alpha, try it on your own, by the way, if you want. Then when you'd hit a roadblock, you'd hit a point where you couldn't go on anymore. So that you essentially need a third equation, and that's this equation. And this equation ties everything nicely together. And this is just something that you got to understand. You got to understand that if I'm rolling and I'm not sliding, I'm not skidding, then this necessarily must be true. Okay, the speed of the object, the translational speed, must be equal to the object's radius times its angular speed. Okay. And if that's true, then I can generate this equation here, solve it for the time. Because notice in this equation, I have mu k, I have g, I have v naught, and time. Time is the only thing that's not on my list here, but it is also something that I need in this first kinematic equation, or the second kinematic equation number 2. If I plug the time, an expression for time in there, then I can figure out the distance, and everything else will be stuff that I can have in my answer. Right? This is a complicated problem, I'm not going to lie. Which is why I totally messed up on purpose, though. I was just kind of showing you my thought process. Just testing it. No. I guarantee you, though, try it the way that I kind of started us down that road. Try it, give it a shot, and you'll see that you'll eventually hit a roadblock. Okay. Now, notice something here, though. Because I got 3 terms here, but I can make this, I can simplify this equation quite a bit and have it only 2 terms, because if I notice, these 2 are 2 words. First word, like.
Like terms.
Well, these are like terms. I have 1 times mu k gt. Here I have 5 halves times mu k gt.
So it's 7 halves mu k.
So it's 7 halves. So if I add mu gt to both sides, I get that the initial velocity is 7 halves mu k gt. Oh, right, like this. Which means that the time is 2 times v naught over 7 mu kg. Right? Make sure I'm not 2 v naught or 7 mu kg. Yeah. There we go. All right. Now if I look at the first kinematic equation number 2, but the one I've written here, final position, initial position is just going to be 0. V naught can be in our answer. T, I can now express in terms of things that can all be in our answer. Acceleration, I have an expression for the acceleration here in terms of things that can be in our answer. And then the time squared, well, this I just put it in squared. So a lot of algebra here, a lot of nasty algebra, but it's not like that's anything new for this problem. So, let's go ahead and, I might need this space. Let's go ahead and write that. Final position equals initial position of 0. Initial velocity times time plus 1/2 the acceleration times time squared. Final position is initial velocity times the time, which is 2 v naught over 7 mu kg, plus 1/2 times the acceleration, which is negative mu kg, times the time squared. Now when I square this, I get 4 v naught squared over 49 mu k squared g squared. Now, like in kinematics, these should be like terms, right? Because you're able to add them at the end. So these should be like terms as well.
Oh, you can cancel.
Yeah. Mu k, let me do it in red. Mu k here cancels with one of those. G cancels with one of those. V naught and V naught makes V naught squared here. V naught squared. Mu kg, mu kg. So we'll be good. So this is going to be 2 V naught squared over 7 coefficient of friction times G minus, I cancel this 2 with that 4, leaving a 2 in the numerator, minus 2 v naught squared over 49 mu k g. You guys can do that, right? You can combine those terms.
Just multiply.
12 over 49. Yeah. So that would be 12 v naught squared over 49 coefficient of friction times g. That is the distance that it will travel before it starts rolling without
Easy
skidding.
enough.
Easy enough. I totally, yeah, no. When you substitute in A over R for angular acceleration, you end up not being able to generate an equation. Maybe you can throw this one in at the end, but I feel like, and on your notes, the same problem is solved. I feel like this is for me, the most straightforward way of solving this.
Imagine if we didn't use 2 bits mr squared.
That would be terrible.
Who doesn't want to imagine that? Did you hit record?
What?
Did you hit record?
Oh, no. Yeah.
I think you just